Okay, welcome everybody. It's New England Dynamics and Number Theory seminar. And today the speaker is Johannes Schleischitz from Cyprus with the title Exact Uniform Approximation and Dirichlet Spectrum. Go ahead.
Thank you for the invitation and the introduction. What I'm going to talk about today is based on this archive preprint that you see. The version 3 is actually not out yet, so there are still a few more, essentially one more result that I present you today that is not in the current archive version, so I'll update it soon. So the outline of the talk is first a short introduction about Diophantine approximation, especially with uniform problems and Dirichlet approximable vectors, because that's what the talk is mainly about. Then some more results about this Dirichlet improvable vectors and Dirichlet spectrum, and some ideas of the proofs of the new results. Okay, so for those who are not so familiar with Diophantine approximation, I have a quick introduction. So basically we are given, I call psi my real number always, and given some parameter q that you could think of as large normally, you want to approximate psi by rationals, and the denominator shouldn't be too large. So p over psi minus p over q absolute value should be small, and you have an absolute bound on small q, capital Q, and how small can you make it in terms of capital Q? And then there's this Dirichlet theorem from 19th century that tells you that you can make it as small as Q inverse times big capital Q inverse, in particular smaller than this denominator to the -2. So this system has always a solution. The most fundamental theorem in Diophantine approximation. And also in this talk, I will mostly use rather the linear form. So equivalently, you can look at the system I wrote below with q theta minus p, which is a linear form. And then the theorem becomes, as I've written here. So this always has a solution in integers p and q. In higher dimension, just to set some notation, this double bar means the distance to the nearest integer for one, for a real number, and for a vector I also use the same notation for simplicity. So the maximum of the distances of any coordinate from an integer. Okay, so it's like taking simultaneous approximation with respect to the maximum norm. And then the theorem from the slide before, you have to replace the exponent. Yeah, and I work in dimension m. M will always be the number of variables. Yeah, and you have to replace the exponent by -1 over m in general. For m is 1 just becomes the theorem from previous slide, but this is more general now. For m numbers, you always have a solution to this. And often we use a corollary which says that q psi has distance at most q to the -1 over m infinitely often. But here there's some information loss happening, of course, and when in this talk it will be important that we are mostly concerned with the more general version with the parameter capital Q. Okay, so if there are no questions, I will go on. So the question is, how can we maybe improve on this Dirichlet theorem for all or certain psi vectors? And for almost all we cannot. So when you write the parameter c as a vector, then this will generically not have many solutions. So for most psi in Lebesgue measure sense, the system with the c smaller than 1 will not be soluble anymore. Yeah, this is from the late 60s. And we call a vector C Dirichlet improvable if this one has a solution for all large Q. And I denote the DIM of C, this set, and if there's just any C for which this is true, so which is the union over C smaller 1, then this will, I just write DIM index, and this is the usually referred to as Dirichlet improvable vectors. And yeah, just a remark, the analog for ordinary approximation of this theorem above would be false. So the inequality, the last inequality would have normally infinitely many solutions. You can even take some C as some function which decreases to 0 not too fast. So this is this Khinchin-Yannick theory. So uniform approximation is really a bit different from a metrical sense. So let me go to the next slide. So yeah, additionally, I want to call badly approximable vectors, which are now, according to this non-uniform setting, this ordinary approximation setting. Yeah, most of you probably know it. For those who don't, you have the reverse inequality kind of. So for some C, so you cannot do much better than Q to the -1 over M. The C is of course smaller than 1. For 1, it will always have infinitely many solutions, but for some small C, when Dirichlet's theorem is almost optimal, then we call Xi badly approximable, and this set I denote by bad M. And why do I do that? Because it turned out, which is not clear at all, but it turned out that every badly approximable number is in uniform approximation kind of a good approximation number. In other words, the bad M set is contained in this Dirichlet improvable set. So we have a big set of Dirichlet improvable numbers because the bad approximable numbers have turned out, again, a non-trivial result, but has been known for a long time by now, that these badly approximable numbers have full dimension M. So also the larger set then, of course. Okay, it has measure 0 still, but full dimension. This is kind of occurs often in Diophantine approximation to have such sets. And yeah, as a remark, if I restrict to a fixed set DIM of C, so for some fixed C smaller than 1, then the Hausdorff dimension is not quite M, but this dimension grows to M when C goes to 1. So I gave 2 references. Maybe there are more that I should give, but Jung, Chevalier, Kleinbock, Mirzadeh. Good, so then I would go further. Just some words on M equals 1, which I will not talk too much about. Okay, there's some bracket missing, but so the set of the badly approximable, no, it's not missing. It almost exhausts DIM. So the theorem is that for M equals 1, the bad approximable numbers and the rational numbers are exactly the Dirichlet improvable numbers. So there's not much more happening than bad. The rationals are kind of clear that they are contained. Right? It will be 0 at some point, the approximation for certain Q. And yeah, if for one-dimensional numbers, you can also characterize the badly approximable numbers in terms of partial quotients in the continued fraction expansion. So all of these results are from the late 60s, as you see. And an even much earlier result tells you that for an irrational real number, again, the setting M equals 1, when you put C is equal to 1/2, then it will not work that this has a solution, at least for a certain large Q. So for 1, of course, again, it's Dirichlet's theorem, but if you in place of 1 by 1/2, then it will not work anymore for certain large Q. I mean, here for certain arbitrarily large Q, I mean, okay. So in fact, this in the notation from before, this di of 1/2 is only Q, and everything else in this what I will call Dirichlet spectrum for one-dimensional will happen for greater than 1/2. Okay, so this is just a quick summary, but most important for this talk will be m greater than 1. And there it turns out that there's not just the bed, the approximable, and the rationals. It's a bigger set, and it contains these so-called singular vectors, which are, yeah, as you see, for all large Q, this system, when you write, okay, I wrote C before, here I wrote epsilon, maybe I should also have written C. Has a solution Q for every large Q and for every no matter how small epsilon is. That's the point here. So, and this set I will denote by sinc M. And it's contained in the Dirichlet approximable numbers by, you see this, the Dirichlet approximable are the intersection of all positive DIM of C sets, and the Dirichlet approximable are the union of all C smaller of this large growing sets as C tends to 1. So this is an obvious conclusion. And another thing that's obvious if you think of it, the Dirichlet approximable. I think that's wrong. Oh, sorry. Bed M.
You meant bed approximable.
Bed, I mean, sorry, that's a mistake again. Bed M and sinc M have no intersection. Sorry, this in the right inequality, right hand side, I mean bed M. Okay. And we have sinc 1 is Q. That's what we saw before, right? But even for 1/2, for 1/2, you would get only Q. And but it turns out for m equals 1, this is a greater 1. This is very different, which I will talk about on the next slide. So totally irrational here means that the coordinates of the vector are linearly independent together with 1. So the classical setup in the Diophantine approximation, that you don't want the vectors to lie in some rational subspace. But there exist many singular vectors which are not in such subspaces. So maybe this has been known before, but I think this Kinshin reference is correct, at least from 60s. And much more recent is a metrical result that it has the exact dimension is known.
Well, I think Kinshin's reference should be in the 20s. Kohler will, of course, correct.
In dimension, there is a story. The first result for dimension 2 is 26, I think.
26. Okay, because I think
there is a story. There is a story. I will not speak about it now.
Okay.
Okay, so yeah, maybe I copied it wrong. Yeah, so it seems a bit too late now that I think about it. Yes. Okay, so but anyway, we know, and in fact, this singular vectors also, as the limit as C towards to 0 of these decreasing sets, the IM of C, in a limit sense, this is also the same value. So yeah, so you approach this value as C tends to 0. This is a consequence of this paper. And another result that I only sketch, I don't say the exact conditions, but on certain manifolds and fractals, there exist singular vectors from a recent paper, Kleinburg, Moschewitz. And there are some other references. I cannot or don't want to talk about everything, so I leave it at this point. So the problems that remain from what I told you so far is this set bed without DIM, without bed and singular, which we know the inclusion, but is the different set non-empty? This is so far not clear. I will talk about this in a second. And then another kind of independent question: how close can we prescribe uniform approximation, especially close to the function q to the -1/m. And this leads us to define this Dirichlet spectrum. So yeah, a Dirichlet constant is what I wrote within this bracket. So take the lim sup of q to the 1/m times this approximation function psi q, which you have in the last line, which is just the distance which jumps downwards towards 0 at certain integer points where you get the beta approximation. And taking this lim sup, we call this Dirichlet constant. And finally, considering or sometimes you restrict to totally rational. Here I wrote or Rm. It shouldn't make much difference, I think. This is always by Dirichlet's theorem a subset of 0, 1. But is it or 0, 1, which turned out to be true for m at least 2? So at this point, these two questions I would say are open. Okay, so maybe you want to record to notice this, memorize this fs of m and d of m. And yeah, essentially this Dirichlet spectrum is like the Lagrange spectrum, if you are more familiar with that, but with respect to the uniform approximation problem again. Okay, because you take the lim sup. If you would take the lim inf instead, then this would really just become the Lagrange, multidimensional Lagrange spectrum. But lim superior means kind of taking the uniform problem, and then we call it Dirichlet spectrum. Okay, the first question, so let me see here the first question. The set is really uncountable. Beresnevich, Guan, Marnat, Ramirez, Velani, 2021. A few words about this. So the proof, first I should say it's unconstructive and based on some result on parametric geometry of numbers, which prescribes several successive minima exponents, not only the first. And yeah, so you only get uncountable, you get no metric reclaim. This is also maybe good to notice. And yes, another remark, it works in the linear form setting because Ra works in this linear form setting, but yeah, Marnat has a new preprint from this year about, in fact, it can also be done for simultaneous directly, it seems. Yeah, and this theorem is refined in that paper in some sense. So for my talk, most importantly, you can say that dm of c, you can even take out some dim of kappa m times c. And then in fact you don't need this this sinc factor here, right? Yeah, in fact you don't need to write this sinc m then anymore, but it's not force. So in fact you can prescribe up to some certain explicit kappa m your approximation, but this kappa m tends to 0 quite fast as m gets larger. So up to a factor kappa m, basically you can approximate and still land in your set FSM. And there's also some other more information which I don't want to talk too much about yeah, approximation by rational subspaces of some dimension of all dimensions in between is also part of this 2021 paper. Yeah, some previous results record how we defined it. Then yeah, for m equals 1, I said it's kind of a difficult set. In fact, it has 0 and otherwise it's contained in 1/2 1. And I just give you some references, but for the sequel, I will always work with m at least 2. So this is always the theorem that I mean before by these 5 authors. A consequence of this is that the Dirichlet spectrum is not too sparse. So with this kappa m from the last slide, if you remember, there's when I take such an interval kappa m is smaller than 1, up to c intersected with dm, there's at least 1 point. That's what you can say. Yeah, at least something. And yeah, I think that similar results can also be inferred from this Cheung-Chevalier result. Should be possible by some metric means. Something, yeah, at least for small c, but I didn't look too closely to it in it. Yeah, so let's say some more things that were known before my new preprint. So let's say we take other norms and let's just generically call it dm with this tilde. When we use another norm, let's for the moment think of the Euclidean norm. Then for the 2-dimensional spectrum, it is known that it is some interval which in some sense as large as it can be. So Nikolai knows much more about this. But yeah, so you can write always an interval where this dm is contained. And in this case, this turns out to be the largest possible interval, where as large as it can be. And another recent result is that when you restrict this tilde set again with the Euclidean norm, then and you work in the subset of the bad numbers, then it's still the whole interval. And when you intersect it otherwise with the bad numbers, then it's dense at least. Might be everything, but I think that's not clear. And some more research, Glenn-Bogarau, structural results, which I don't want to record in detail, but on this tilde set with respect to, I think, arbitrary norms or maybe some restrictions, but very general at least. Yeah, maybe one more word, this bad intersected with bad set. This is an interesting question where I will say nothing about. So would be really interesting to know if, let's say, without tilde also, what would appear here. I don't know. I would rather work in this now always with this set where I exclude the bad numbers. Yeah, and what I should say from my no new preprint, it will follow, in fact, that for certain norms, you always have some inclusion. So for this, the Euclidean norm, it's not quite the result from above. This interval I2 is larger, but you have always, for a large number of norms, you always have some interval included in the DDM. For example, P norms I can take. Yeah, especially the Euclidean norm. Okay, now I come finally to the new results. So I denote, as usual, dim packing and dim H, Hausdorff and packing dimension. So I will not record the definitions. You can think just of some dimension which is not necessarily an integer. And I will also use this thick LM set for the Liouville vectors, which are kind of arbitrarily well approximable with respect to ordinary approximation. So you see the definition here. No matter how large n is, you always can solve this in Q. Yeah, and they should be irrational. I said normally you want them also. You don't consider rational vectors also have this property that you wouldn't call them Liouville vectors. So let's say Rm without Qm. And it's clear that they are on the completely opposite side of the spectrum. So then the badly approximable numbers, so they have empty intersection with bad. Okay, so what's the new result now? The first, for M at least 2, the Dirichlet spectrum is as large as it can be. It's the whole interval, 0, 1. And I also get some, yeah, here I talk about packing dimension so far, some packing results. So basically, there are numbers that have exact Dirichlet exponent C. exact exponent C, and also are Liouville vectors. And this set still has a rather large packing dimension. So it's m-1, which is a pretty good bound, I think. So in particular, the bound is independent of C. And for small c, it seems to be close up to addition of 1 over m plus 1. It should be optimal. This seems not to be quite clear, but it's suggested by this preprints of, or one of them is published, of Das, Fishman, Simons, Urbanski. So we are really quite close to what should be expected. Okay, any questions so far? Okay, then I go on. The second result is now I come to Hausdorff dimension, which is more widely used. Here, so this result, this set is rather similar than what I had before. So again, basically, I take this first bracket is just the set of numbers with exact Dirichlet constant C, and that are not badly approximable. In particular, they are of course not singular when they have exact constant C. And this, when I call this set FMC, then again, I can show that it also has positive Hausdorff dimension, and I can even up a lower bound. I mean, it's possible to write down an exact bound, but it would get not too nice. So, but asymptotically, it would give you, for large M, something like 3 over 8 times M. Okay, so here the conjectures are a bit further away, of course, from my result. So we should expect that, again, the same bound should happen, should maybe be correct as C tends to 0. But here the bound is really settled. Not for the packing dimension, it was not quite clear, but here it's clear that this is an upper bound, but it's quite far from 3 over 8 times M, right? M-1 is almost M. And as C tends to 1, in fact, you would probably, but my guess would be that it's the same as the Hausdorff dimension of the IM of C, which should be of, which is of form M minus small o of 1. And the second one generalizes a conjecture of where this DIM of C is not taken, but yes, just this FM, this Fs of M is taken conjecture to have dimension 1. So this is would generalize this conjecture. So to sum up, some Hausdorff dimension result, which is not as good as the packing result, but still at least positive and tending to infinity, but probably further away from the expected values. Okay. And finally, the last, or not quite the last, but again, something about Hausdorff dimension, but where I introduce also these sets of exact order of approximation, lambda. So let lambda be a value between -1 over m and infinity, can be infinite. And yeah, this lambda is the uniform, the ordinary exponent of approximation for which this inequality has infinitely many solutions. So that's why I take 1 over m. By Dirichlet's theorem, it's always satisfied for 1 over m. But it might be larger, and these sets will decrease. Right? Again, they are not. I want exact order. That's important here. Not lower equal, but really equality. They should have exact order of approximation lambda. In particular, by this definition, it follows that the bad set is a subset of when lambda is 1 over m, and the Dirichlet vectors are just defined. I defined before were just the infinite case. And then the result is when lambda is not too small, like 1.61 something, so golden ratio -1, then I can intersect my set from before. So maybe I recall It was this set FMC, exact Dirichlet exponent C and not bad, with this set Wm lambda, and it still has positive Hausdorff dimension and still explicitly computable bounds. And you have some kind of asymptotics. So if you think of large M and large lambda, basically, then you have something like M over 2 lambda. Okay, and this is not so far from, I mean, up to a factor, not close to the truth. So what because Wm alone, this subset, this superset, Wm of lambda has dimension roughly M over lambda, so I'm only differing by a factor 2. So yeah, when I intersect. And in fact, the theorem is also true for lambda greater 1, but in the paper I decided the proof is a bit messy, so I didn't want to do it too exactly. I just give a rough idea, but in fact, lambda is equal to with greater 1 would also be enough for everything I said. And the conjecture would be that this map is decreasing, but this is not. Yeah, this is a conjecture. Yeah. So given a fixed C, then you would naturally expect that because Wm clearly decreases, as you see in the first displayed equation, then you would still expect it for the intersection.
Is it continuous?
I would guess so. Okay. Yeah. But yeah, I don't know anything about it yet. So. And yeah, some remarks to the last theorem. So maybe I go back. So this intersection set is large, we said. In fact, I can take more general functions. I only need, so when I already take the beta exponent 1 instead of this Gordon ratio -1, I can take any function that should model my ordinary decay, and then take the psi that are really up to a factor 1, basically these lower points I know how they decay. Then we can do the same with this special set, okay? So, and the Hausdorff dimension to be positive, of course, I need some control on the decay. If it would decay faster than any negative power, then again, by this Yannick theorem, the dimension is automatically 0. But in any other case, when you have some bound, then the dimension is also positive. And so you can prescribe the approximation in a much finer way than just giving the order of approximation in terms of exponent. Yeah, so we can prescribe uniform because of this C, right? And also the ordinary approximation, so both at once up to a factor as good as possible. Yeah. And I want to mention also some related result. I had this before, this new paper from Marnat. He got something similar, but he only got uncountably again instead of the Hausdorff dimension result. Then for he considers special psi, he only gets a fixed factor, so he cannot go up to 1. So it's this kappa m is kind of small. But an advantage to my result is that I need still this decay property in 2, and he has this natural decay bound. Lambda is just greater than 1 over m. That would be the ideal outcome to press it down to this. Okay. Yeah, my theorem, I prove in fact a theorem which is a bit more general than. I don't restrict to this function c times t to the -1 over m, but want functions that have these three properties. So the first one is just very natural from Dirichlet's theorem. The second one tells you that it should not decay too fast. So basically at least like 1 over m minus 1 in the exponent. So you make it a bit, the decay, but still there's some space in between 1 over m and 1 over m minus 1. If it somehow is in this range. And the third condition basically says that it shouldn't decay too fast in short intervals. So when you take, for most functions, this is, all three are, these three is also satisfied. So some class of functions, clearly every power function like this satisfies these properties, or you can multiply with lower order functions like iterated logarithms. They all satisfy these properties. So it's not very restrictive. And okay, for the next slide, I want to again remind you what my approximation function psi was, which modeled the approximation as you go within capital Q. And for these functions, I can still have basically the same as I had for the special functions, c times t to the minus 1 over m. So you can approximate always by as good as psi. And for certain large Q, you have the reverse inequality by an factor arbitrarily close to 1. And then you have uncountability. And if you again assume some lower bound for okay, I mean the lower bound 1 over m minus 1 is clear from D2, if you say D2 here. So you always also get, in fact, some positive packing dimension, and it's just m times 1 minus this gamma that I can take here. And also positive Hausdorff dimension, which is again computable, but not so nice to write down. And yeah, in fact, the bound is, this gamma lies in fact in a very small range between 1 over m and 1 over m minus 1. So the bound is optimally m minus 1 and can be a little bit smaller than that, but it's not too far away from n minus 1. So for all these functions, I get almost the same result as for the special functions. Okay, then the last new thing I think is I can also work with these counter sets K, which are the n-fold, the n-fold Cartesian product of these classical counter sets, where you only use the digits 0 and 1 in the. I can also give a version with more general digit sets, but for simplicity, let's say we have digit 0, 1, and in base B expansion of a real number, we take this set and we take k-fold or m-fold Cartesian product. Then we have still very similar results. We just have to weaken the approximation property a little bit, so you cannot prescribe up to a factor 1, but some other factor, and the metrical results will become, of course, must change when the set has smaller dimension. So the result is the following. Again, independent of this C between 0 and 1, you can intersect the set that we had before almost, but now you have a factor b to the minus 1 over m. So you cannot go until 1 minus epsilon would be ideal, but you have another factor b to the minus 1 over m, and then you intersect the whole thing with the counter set, which is part of this folklore set intersected with k. Then the result is very natural. You have again the same. So if the dimension of k would be full, then you would again get this m minus 1 again. So you have a very plausible result for the packing dimension. And also some positive Hausdorff dimension result, which is not so analogous to the real case, but still you get something positive. And yeah, it turns out this turns out to be easy to prove because my construction is very close to considering such sets. Okay, so these are the new results. I just want to mention one more open problem. Again, take the counter set as before, but now, yeah, it can also be interpreted as coming from an iterated function system. Yeah, with certain functions, rational affine functions, and now a problem I would suggest is, or that I noticed also wrote down in the paper. Is it true for in a more general situation like this that K intersected with this folklore set is non-empty or maybe even metrical results, or at least for some nice IFS where you take rational matrix and rational shift vector, if it's not too trivial, so that's why I wrote uncountable. So yeah, then maybe this is true that in general, but maybe hard to prove. Okay. So I come to the last part where I sketch give some proof ideas. So I recall what I stated first. So this packing dimension result for numbers that have exact Dirichlet exponent C and are also Liouville. So first, yeah, I give just a rough ideas. So call this set within DIMP, let's call it omega. Then, yeah, the first idea I had was to construct some number, and much later only I saw that in fact some metrical claims can be stated too. So the first thing is to construct just one number, or uncountably many is then not too hard. This is standard. But yeah, the metrical claims also use some kind of variational argument, but it's a bit not that straightforward maybe. And more precisely, we construct some kind of counter type set again, which is in this contained in this set, which and then we need to finally estimate the dimension of this counter set. And I use some result of Tricot from the 80s for that. Yeah, because I have packing dimension here, right? So that this turned out to be useful. So yeah, so let's talk about the existence of such Dirichlet constant exactly given and Liouville. So I take some sequence where that grows fast, and one an divides an plus 1 for all n, and it's constructed as follows. When I have the first m terms, let's say, I get the next m terms in the following way. I take the last number that I had and raise it to some large power to get am plus 1. So there will be huge gaps between in here. This will cause the vector to be Liouville also directly. And then I take powers of this new number, am plus 1, square, cube, and so on, up to power m minus 1. And in the last step, I do something slightly different. I again want it to be roughly of this size, m's power. But because I have this to obtain finally the constant c, it turns out basically I have to multiply with c to the m. And because it should be a multiple of this. Okay, I think I have to do it slightly different. It should be a multiple of this previous term. So I think the c to the m, this m minus 1 should probably be at the other term. But anyway, basically that's the idea. So I want it to be of size c to the m times the factor c to the m will give me basically that I have constant c. Okay, and having this sequence, I simply take the sum over the reciprocals with, in the residue class I modulo m for every I. These are the coordinates of my vector. And it turns out that, it has the properties that we want. And and the proof is elementary, but you just have to do the right things, but it's nothing deep happens. It's just distinguishing some cases, and it turns out this construction just works. This LM is kind of clear from the property, as I said, from the first property that Mn is large, and that it has Dirichlet exponent c is of course the main part of the theorem. And for this you have to work, of course, but I will not say too much more about this. But now, having found some numbers like this, how can we get a good packing dimension estimate? So for the moment, think of powers of 2 for this sequence that I constructed before. So Cn is then an increasing sequence, fast increasing sequence, and this xi are of this form, which you can think of the binary expansions. And then it turns out that the argument still works when you replace some digits in intervals like this. And these are large intervals, because we had a long gap between Cm and Cmn plus 1, Cmn and Cmn plus 1. So these intervals are really huge, and whatever digits you put for all the xi, it will not affect the construction. It will still work, it turns out. And this variation will give me finally something. So it induces some counter type set within omega. Omega was the set that I started with. And now we only need to estimate the counter dimension subset, but we are talking about packing dimension, so I need something else. So for the estimate, I use this Tricot estimate, which is the last, this 3. Okay, no, that's what follows from it, but that I really use. So Tricot's estimate is the second line. Then the first line is also clear from, because it's from the product to the sum, because it's a continuous map. So this is also, so the first 2 lines are, the first is a well-known property for Hausdorff measure. The second is this Tricot result, which is not so trivial. And you get finally this 3, and this is true for every subsets AB. And then we want to estimate this counter set C from the last side. We put that A. And then we need to find, according to 3, we need to find some set B where the sum set is large and the Hausdorff dimension of B itself is small. Then you will get a large right-hand side. And if we have this, then you get that the packing dimension of our set that we want is bounded clearly below from the subset packing dimension, and this will be Rm has dimension m, and the Hausdorff dimension of B, in fact, it turns out I can take, it works with 1, so that's how I get the bound m minus 1. So some variational principle plus Tricot's estimate, plus some construction which I didn't talk in detail about here. But basically you get this B will be a set of very well approximable numbers. That's how you can, that's why it will have, by this Janik-Besicovich type results, it will have a small dimension. Okay, so that's the proof of the first theorem. And if I have a bit more time, maybe I state again the second one, which was on Hausdorff dimension. Again, I construct a counter type subset. it's again some digital based construction, which is a bit more complicated than the one before, but still there are some intervals where you have 3 digit choices. Here I cannot take subsets of the Liouville vectors because they have dimension 0 and I want positive dimension. So that's just a remark. And then to use this, I again want a lower dimension for this Cantor set host of dimension. Here I have to optimize some parameters and work with the standard tool from the next slide. Yeah, so the host of dimensions of the Cantor set are bounded by some lemma from Falconer's book, which is kind of classical again. So you have some interval construction, like in the Cantor set, where you have a decreasing, some nested sequence of sets. And in each step, you divide the given set into a number of subsets, and you are given how many subsets there will be, mn, and in step n, and you also know by how much gap you will have between this, denoted by these epsilons. And then you can bound from below the host of dimension, and in many natural settings, this is in fact an equality. And yeah, I use this. The digital restrictions give me such a setting with certain sets EI as in the theorem. I get these m's and epsilons with it, and plugging in and optimizing some occurring parameters will give me the result 3/8m. Yeah, and in the last slide, work in progress, you can say future plans. So I have 3 main directions I want to manage. So firstly, it should be relatively easy to get the same results for p-adic vectors. And this is can be interesting because this result by these 5 authors that I talked about a lot is related on this parametric geometry of numbers, and it's not clear how to do it in p-adic case, but it's an advantage of my method that it's rather easy to. There's some things need to be done, but it's still kind of straightforward. Yeah, again, you can define Dirichlet improvable and bad and singular as for real vectors, and the same results will hold. And the next set is a little bit more difficult, but still shouldn't be too hard. A weighted setting. So I wrote in precisely what the exactly approximation by weights for simultaneous approximation means. And again, I want finally that some set FSM of R of this weight vector, meaning that they are weighted Dirichlet improvable but not bad or singular, or in a weighted sense. Okay, so this also seems doable with the method, with some modifications. The last thing, which is not so clear if it will work, you can define also systems of linear forms. This n should be the number of variables of the linear form, or matrix setting if you prefer. And you can ask very similar questions. And here this seems to be harder to generalize it to this setting, because even for one linear form, I think I understand now what happens for one linear form. But even 2 times 2 is already not so clear, but maybe it can be done. And yeah, combining 2 or 3 was again explicitly mentioned in this Beresnevich, Guan, Marnat, Ramirez and Velani paper to solve the combination of 2 and 3, where S is again some weight vector for the psi. How can I say? So you have 2 kinds of vectors of weighted setting here with respect to the q psi, and also with respect to these q's which are not the same, right? So you would have two doubly weighted in some sense. So this would be the ideal outcome, to have something like this, and also some metrical result that would be ideal. Okay, I stop here. I think it was long enough anyway. Yeah.
Okay, well, thank you, Hannes. Let's give you a round of applause. And maybe there's, well, we certainly have some time for questions if anybody wants. So if you allow me, can you come back to? So I think the crucial point is where we construct some vector.
Yeah.
And then you say that this vector has precise exponent c. Not exponent. This point in
Yeah.
Dirichlet.
Where do I have it? Yeah. Yes, I think this slide you're talking about. Yeah.
Right. So Dirichlet exponent c. So can you explain briefly why you said it's a long story, but maybe you can give some idea?
Yeah, I mean the gaps. Yeah, I mean, so basically the gap between there are long gaps between this or when you think of it at the logarithmic level, like with these c's here, there is some large gaps between this cn. And this gives you good approximations. So proving that the lower bound, I mean, that there are always good approximations is, yeah, then kind of really straightforward. The main problem with such constructions is mostly that to show that there are not unexpected beta approximations, but I use special parameters capital Q. And for these, yeah, maybe I could have given more detail without. So basically, it relies on some very easy principle that when you have some vector with p over q, which is not an integer, then it has at least distance 1 over q from any integer. And using this very obvious fact in some, this is what I use, but in a concrete setting, it turns out to give exactly what I want. So I need to have some case distinctions. I don't know, without slide, I'm not sure how much more I can say that it's understandable.
I see, but basically here you have the proof that Dirichlet spectrum is the whole interval from 0 to 1.
Yes, because
you only interested in this statement, and
yeah, the c to the m here, I mean, this looks a bit different because I do it for general phi in my general functions in my paper. But if you would break it down to this, just wanting Dirichlet exponent c, what you would use is, yeah, you got the c because of this last step, basically. This vector c to the m for given c will exactly turn out to give you that exponent c in some sense, yeah. So you have just to modify the construction where you just take the m's power by a suitably constant to get some exactly the right c that you want to start with.
Okay. Interesting. Maybe I should look at the paper and think about it some more. Any other questions?
Yes, I'd like to ask also a question about this. In the first paper by Akonjanov and Shatskov 10 years ago, where they construct a specific vector for a specific value of the spectrum, so they know more than just the limb soup. They know at each step, I mean, in terms of the best approximations, they know what happens at each step. I'm not being that precise because I can do it.
Yeah, the best approximations. Yeah, they know more about the best approximation. Okay,
yes.
I see.
So in your construction, do you know also about what happens at each step, or what happens only at soup?
I think I don't have a complete description of all best approximations, but I know, but I have an idea. Yeah, I mean, I know where the good approximations occur. the ones that will induce this Dirichlet exponent. So I have a relatively good understanding of the approximation picture, but maybe I can't say exactly what all good approximations look like.
Mm-hmm.
So partly, so I would say I have some information, yes, but not a complete picture.
And another question is for a general norm or for the P norms that you've said.
Yeah.
You do the similar construction, or you deduce it without this construction?
Yeah, basically what I do is I sum up integers. Here I sum up reciprocals of integers, and in the p-adic norm I will everything should be very similar. I take p powers for this a's. So instead of 2 to the cn, I write p to the cn, of course, for p-adic, and then I don't take reciprocals, but just sum up integers. Right? In p-adic, this makes sense, and it turns out that that this should be enough. The proof is a little bit different, but the motivation is the same. Yeah, you again see the good approximations where they occur, and you can estimate them, and it should give exactly the same. Yeah.
And if you take a general norm, so this kind of a construction, you think can work?
Okay, are you talking? I thought you're talking about p-adic. Okay,
no.
You mean the general norm? Okay,
yes.
I misunderstood. Okay, no, what I was talking about was p-adic. For p norms, yeah, it follows because I know something about basically for p norms. Yeah, because I know that one element, this vector will look for good approximations. There will be one component which is like the leader, which is much larger than all the other components. So the p norm is in fact not so much different than the maximum norm. That's the point. So if I take my vector q psi, this vector, where do I have it? Maybe I have it written somewhere. Like in this q psi vector in the second line, if I take this, then there will be one component which is much larger than all the other components. So in fact, taking norms will not, other norms, if the norm is not too bad, then it shouldn't change too much. So I think maybe even for general norms, I can say something. Yeah.
But here you have function psi which goes to 0 quickly, t-1.
No, I'm not talking about. I just wanted to talk about that. You see this q psi. I'm not talking about this. I'm still talking about uniform approximation. I just wanted to took this slide because here this q psi occurs. Okay. Yeah. The point is that the vectors that are small, the good approximations, have one component q psi 1, say, that is still much larger than all the others, and then it doesn't. Then taking another norm doesn't. It's almost like taking Euclidean and maximum norm is almost the same when all the other components are much smaller. That's the point.
Yeah. Okay. Well, other questions? So I just have a general question. You talked about vectors and you talked about linear forms. Well, you didn't talk about linear forms, but you could talk about linear forms or even systems. So if you compare Dirichlet spectrum for vectors and for linear forms, are they the same?
Yeah, that's a good point. I didn't want to mention it still because I thought the talk was already so overloaded. But I have also in the appendix of the paper, I talk a bit about the case of one linear form. So what's a direct consequence of the result that the Dirichlet spectrum for simultaneous is everything, is that I can, in fact, okay, let's go maybe back to Yeah, I said, let's look at this refinement on this page, refinement for C in 01. So this paper by these 5 authors gives you some kappa m, where this is also not empty, right? But you don't get exact C, but you are miss it by some kappa m. And I get something similar for a linear form again. So I don't get, but my bound will be also, this kappa m for me will also depend implicitly of C. So I don't get just the factor times C. So yeah, the short answer is you can say something about the Dirichlet spectrum, but I can't say that it's 0, 1, at least not directly from my result. It should be true, and I think I can prove it because I have thought a bit about this from another direction, and yeah, in the current paper I only give some result which is similar to this refinement result here.
Okay, but in general, if you fix a vector, so you have a vector and it comes with this Dirichlet constant, which is lim sup of something.
Yes.
Then what can you say about the Dirichlet constant of its transpose? Nothing?
Yeah, no, yeah, that's exactly what I'm doing. I mean, how I get this result. So in the appendix of the paper, what I do is, yeah, I use some kind of transference results. So
so there is some inversion of transference.
Yeah, so by German I use it. So Mahler did something in this direction, and from German 2012 or 13, he had a bit of an improvement, and I use, yeah, so it's a transference result, which gives you a type of result like in this, like I stated in the refinement. Just, yeah, interestingly, it depends on C. So I don't get kappa m times C for some kappa, but I have to take C to the power m square. So my result gets worse when C gets small. My result is better than this one when C is rather close to 1, but it gets worse when C is small.
But my question was just about transference. So if you so you're using German's inequalities, so you fix a vector. Suppose it has Dirichlet constant C.
Yes.
Then you're saying that transference implies that there is some range of values for Dirichlet constants of the transposed vector.
But just range of values, not exact constant.
Yeah, exactly. An interval. Yeah. I know an interval values.
Yeah, exactly. So just some interval.
Yeah, exactly.
And this is sharp. It's possible to get both ends of the interval.
I don't think so, because this, it's some, Gelman's work, like Mahler's, is based on geometry of numbers, and I think it's still not 100% precise. So you can probably do a little bit, but probably not too much. So this interval can maybe be made a bit smaller with some work. But yeah, then you have to go into this geometry of numbers business. And yeah, as I said, I believe that in fact it should be, for one linear form, it should also be 0, 1. And for this, a transference result will never be enough. So
yeah, of course, sure.
Do you have any direct constructions for linear form to construct vectors with precise Dirichlet constants?
Yeah, that's what I indicated. I thought a bit about it, and I have an idea, and I think I can do it, but I have not written it down yet. Yeah.
Oh, I see.
That's interesting. So let me make maybe one more comment related to the title of the seminar. Probably, I mean, we didn't really pay attention to it, but it's called Dynamics and Number Theory. So let me just comment that you actually proved a very interesting theorem in dynamics without realizing it, perhaps. So what happens here is that you have a certain so you have the space of lattices in dimension m+1, and you have a certain family of subsets of this set of lattices shrinking to some strange set. And what you proved basically is that for any set from this family, you can construct lattices whose diagonal orbits don't enter this set, but they enter its boundary. And also these orbits are unbounded.
Yeah, I mean, I'm not working, as I said, in dynamics, so I'm yeah.
Yes, but
I know that there are dynamical interpretations of these things. Yeah, but I haven't looked into that too closely. But it should be some one-to-one relation, yes, to dynamics.
Yes, so of course there are many questions about possible generalizations of this result in dynamical directions, taking other sets, taking other flows, and so on. But this is just a comment. No specific questions. Any other comments? Okay, well, this was a great Q&A session, so let's thank Johannes again. Like this, and I'll see everybody hopefully next week.
Yeah, thank you.